In Chapter 3, we're going to be discussing valence bond theory and molecular orbital theory. This specific section, we're going to focus on valence bonds and hybridization theory. So first, let's talk a little bit about valence bonds. If you remember, a covalent bond is when we have two half-filled valence orbitals from two different atoms, and they're going to combine and overlap to form our bond. This overlapping of orbitals creates a new orbital that has an increased electron density between our two nuclei. And this is the idea behind valence bond theory, is that we're going to overlap our orbitals to form a bond between our two atoms. So let's quickly review some atomic orbitals again. An orbital just describes the three-dimensional space we are most likely to find an atom in. This is what we refer to as the electron density of the atom. According to the Heisenberg uncertainty principle, we cannot know both the momentum and the location at the same time. We know the momentum of our electrons, so we don't know the exact location of our electrons at any given point in time, which is why we talk about these orbitals, these three-dimensional spaces where we are most likely to find those electrons in around the nucleus of our atom. For each one of our orbitals, we do have some electron phases that we'll be looking at throughout our different theories. An electron phase is an immeasurable quantity, but it's going to play a role in how the orbitals are going to interact with each other, constructively or destructively. We're going to denote our electron phases on paper via shading, where one phase will be shaded and the other phase will not be shaded. We're not going to get very specific in our shading, other than we are going to see that we have some different electron phases as we look at the specific orbitals in our diagrams for both valence bond theory and for our molecular orbital theory. So again, let's look at some of our orbitals. First, we have our s orbital, and this is an atomic orbital. Our s orbitals are spherical in nature, and one orbital has exactly the same phase. So if I look at it in the context of my sphere is going to be around the nucleus of my atom. And the entire orbital has the same phase associated with it. So if I wanted to look at the opposite phase, I would have to draw a different orbital, and I might shade that orbital in to say it's in a different phase than the other one. But again, within the 1s orbital, we only have one phase. The electron density in an s orbital is going to be highest near the nucleus, and it will decrease as we move away from the nucleus. So as we get farther and farther away from the nucleus of the atom, we're less and less likely to find that electron. The other type of orbital we're going to look at for organic chemistry is going to be our p orbitals. Remember, our p orbitals have that dumbbell shape, where our nucleus is there in the middle of that dumbbell. With our p orbitals, the two lobes have opposite phases. So we'll oftentimes see one side of our p orbital shaded and the other side of our p orbital not shaded. It does not matter, again, which orbital side we shade, as long as one of those is shaded and the other one is not. One of the differences with our p orbitals is we have what we refer to as a node. And a node is going to be right at the nucleus. And a node means we have no electron density there. So in the p orbital, we do not have any electron density right around the nucleus. Our electron density is in those two lobes away from the nucleus. We do have three different orientations in space for our p orbital. This would be on our x, y, and z axis. So I can put one of my p orbitals on the y-axis. I can put another one of my p orbitals on the x-axis. And then I would have a p orbital that is going to point out at us and one that is going to point back at us. And I will show the pointing out and pointing back just like we have done previously. I will darken whatever is pointing out at you, and I will dash whatever is pointing back behind us. But do remember we have those three orientations in space for our p subshells. So now let's delve a little bit more into the valence bond theory and what that's going to look like as we start to form our molecules. So one of the things we're going to be looking at is going to be our symmetry. And with our symmetry, one of the types we're going to have is going to be sigma symmetry. And this is where we're going to see the overlap of those orbitals along the internuclear axis or what is oftentimes referred to as the bonding axis. So if I have my two nuclei, what that means is that the overlap of my orbitals is going to be directly on this line in between my two nuclei. And that is what we're going to refer to as being a sigma symmetry, or having a sigma type bonding axis associated with it. This type of sigma symmetry is always going to create for us what we refer to as that single bond within our molecules. So anytime we have our sigma symmetry, we will see a single bond within our structure. So let's look at some examples of this sigma type symmetry. First, we're going to go ahead and look at our example of just H2. So each one of our hydrogen atoms has an s orbital associated with it. And we're going to allow those two s orbitals to come close enough together so that they actually overlap. So there's our valence bond theory, an overlap of our orbitals. What you'll notice is that overlap is in between the two nuclei. It is directly on that internuclear or bonding axis that we have. So then according to our valence bond theory, that new orbital that we have is going to localize that electron density of those two atoms in between those two nuclei to generate this new orbital that accounts for both of the different atoms. I also want to look at our example of chlorine gas, so Cl2. So our valence electrons are going to be in a p-type orbital for our chlorine. So we're going to look at two p orbitals that we have for our chlorine. Once again, I'm going to allow them to come close enough together so that those p orbitals overlap. And what we're going to see is an overlap of two of those lobes, one lobe from each one of our nuclei. And I'm going to shade those lobes in to show our two different phases that we have. And one of the things that we're going to note is that the phases need to be the same in order for us to have our overlap. Once again, it is still on that internuclear axis, so right in between our two nuclei. So once again, we will have that sigma symmetry, and we will also see the electron density now be in between those two nuclei that we have. So a change in our type of orbital once we have the overlap itself. They are going to be in between the two nuclei. We will see single bonds in both of these structures, and they will have sigma symmetry. The problem that we're going to run into is that a lot of this overlap of those atomic orbitals do not actually account for the understanding of the shapes that we talked about in our previous chapter. And they don't account for the bond angles that we see in those specific molecules as well. So we have to come up with a different type of theory other than just an overlap of those atomic orbitals. So what we're going to use is we're going to actually create some new types of orbitals around our atoms. And what we're going to do is we're going to create some hybrid atomic orbitals. These hybrid orbitals are going to be made from two or more atomic orbitals from the same valence shell of one atom. So what we're going to see in organic chemistry is we're going to be combining those s and p orbitals on the same atom together to generate our new hybrid orbitals. One of the rules that we're going to follow is that the number of atomic orbitals that we put into this hybridization process is going to equal the number of hybrid orbitals that we actually get out that will be utilized for bonding and the making of our new substances. So let's look at the different types of hybridization that we can have. One type of hybridization is going to be our sp3 hybrid orbitals. This is where we're going to combine one s orbital and three p orbitals. Again, all on one atom. Since we're combining a total of 4 orbitals, we're going to form 4 new sp3 hybrid orbitals. And all these orbitals are going to be degenerate. Remember, the term degenerate means the same energy. So all 4 of these new sp3 hybrid orbitals are going to have the same energy associated with them. Each orbital is going to possess 25% s and 75% p character when we talk about the shape and the nature of these new hybrid orbitals that we're generating. So what that means is that they are going to look similar to our p orbitals, but we are going to see that they have a little bit of s associated with them as well. So what that means is in our 2 lobes, one lobe is going to be very, very large, one lobe is going to be very, very small. I'm going to shade in the smaller lobe. We're going to see that same type of phase notation where one lobe will be one phase, the other lobe will be the other phase. We do still have a node, a place where we are going to find no electron density. When we look at all four of these orbitals, they are going to align in a different pattern so that we can, different place in space, so we can actually see a three-dimensional shape with all of our four sp3 hybrid orbitals. When we draw in all four of our sp3 hybrid orbitals, we're going to typically ignore that small lobe. It is so small that the electrons are not going to spend much time in that lobe, so we're going to focus on the larger lobe that we have with our sp3 hybrid orbital when we look at them in our three-dimensional space or combining all four of our hybrid orbitals. They are going to orient themselves on the XYZ axis, so I will have one sp3 hybrid orbital on the y-axis. I will have one sp3 hybrid orbital on the x-axis. I'm then going to have one sp3 hybrid orbital point out at you. So I'm going to darken that in so you can see that it is pointing out of the screen. We will then also have one sp3 hybrid orbital going back in behind the screen. So again, I'm going to dash that so that I know it's behind the plane. These four sp3 hybrid orbitals are what account for that tetrahedral electron domain geometry that we talked about in our previous chapter. So there's our sp3 hybrid orbitals that account for the tetrahedral electron domain geometries that we will see. It is also what gives us that 109.5 degree angle that we have within those structures. So it's also what gives us that 109.5 degree angle within our structures. So this is our sp3 hybrid orbitals. We're going to combine one s and all three of our p orbitals to generate these four new sp3 hybrid orbitals. The next type of hybridization is going to be sp2 hybrid orbitals. With sp2 hybrid orbitals, we're going to combine the one s orbital with two of our p orbitals. We are going to leave one p orbital unhybridized, and that will be important later on, that we are leaving one of our p orbitals unhybridized. So we're combining three total orbitals, so we're going to get out three new sp2 hybrid orbitals that once again are going to be degenerate for us. These ones contain about 33.33% S characteristics and 66.67% P characteristic. So once again, we're going to see our two lobes. One lobe is going to be smaller than the other lobe. So once again, we're going to focus on the large lobe. We do still have the node associated with it as well. With our three sp2 hybrid orbitals, they are all going to orient themselves once again on our three-dimensional plane. This time all three of our orbitals, again I'm ignoring the smaller lobe and just drawing in the larger lobe, will account for our trigonal planar electron domain geometry and that 120 degree angle. So they will account for our three electron domains, so that trigonal planar electron domain geometry and that 120 degree angle. So there are our three sp2 hybrid orbitals. What we do have to remember is we do still have this one unhybridized p orbital within our structure, so I am going to draw that in. This is then going to be pointing out at us and going back behind this plane of the board as well. So it'll be going back behind the plane of the screen as well. So this is our p orbital. It will still be there. It does need to be in a different plane. So since I have put my sp2 hybridized orbitals in the plane of the paper, my p orbital is pointing out at you and going back behind the plane of the paper as well. And we can orient these on our three-dimensional axes however we need to with our structure, but recognize that they do all need to be in different planes. They cannot be in the same plane. The last type of hybridization that we're going to have is going to be our sp hybrid orbitals. So these are going to be our sp hybrid orbitals. We're going to combine one s orbital and one p orbital, and this time we're going to have two unhybridized p orbitals left over. So we're putting in two atomic orbitals. We're going to get out two new sp hybrid orbitals that are once again going to be degenerate in nature. With these ones, we're going to see a 50-50% S and P characteristic with our different orbitals. So once again, when we draw them, they're going to have two lobes. One lobe is going to be very, very small. One lobe will be very, very large. We still have the node. What changes is the size of each one of those lobes. The more S characteristic we have, the fatter those lobes become, the more spherical they become. The more P characteristic we have, the longer those lobes tend to become. But they all have this same type of notation of two lobes, one lobe being larger than the other. When I look at their orientation of these two orbitals on our three-dimensional plane, we have one sp orbital on one side and we have one sp orbital on the other. So you do want to be very careful. This does look like a p orbital. What is going to make us recognize that it is not a p orbital is the fact that neither one of them are shaded. So this represents two sp hybrid orbitals. It accounts for the linear nature that we will see in our shapes and that 180-degree bond angle. So it accounts for the linear shape, the linear electron domain geometry, and our 180-degree bond angle between these orbitals. We do still have those two unhybridized p orbitals that are still there, and they do have to be in a different plane. So since I have put the sp orbitals on the x plane, I can put a p orbital on the y plane, and again this is going to be a p orbital, so I'm going to shade in one side and I'm going to leave one side unshaded to recognize this is a p orbital, not a hybrid orbital. The other one is then going to be on the z-axis, so I'm going to darken in one lobe, it's pointing out at you, and then back behind the plane of the screen is the other half of that p orbital. So we have two unhybridized p orbitals within our structure. Again, we have to pay very close attention that these orbitals are on different planes. They are not all allowed to be on the same plane. So with our hybrid orbitals, we can still talk about our symmetry, the way that these orbitals are going to overlap. So we are still going to see that sigma symmetry, which is going to be the overlap of the orbitals along that internuclear axis, and this sigma symmetry will still create our single bond. The only difference that we're going to see here is that we're going to be using these hybrid orbitals to generate our sigma symmetry instead of our atomic orbitals. But we'll still see the overlap directly in between our two nuclei. When we talk about hybridized orbitals, we can have a second type of symmetry, and this is going to be pi symmetry. Pi symmetry is going to occur when the orbitals overlap on opposite sides of that internuclear axis or the bonding axis. These are specifically going to come from our unhybridized p orbitals. So these are specifically going to come from our unhybridized p orbitals. So when our p orbitals are on any plane or any axis other than the x-axis, they can still overlap. So here's our internuclear axis, my line in between my two nuclei, and you'll notice the lobes of my orbital are above and below or opposite sides of that internuclear axis. This is where we are going to see our overlap. So I will see an overlap between the lobes, and let's shade them in, between the lobes of our p orbital. This is what we refer to as pi symmetry. When the lobes get close enough to overlap, they will overlap above and below the internuclear axis, because on that internuclear axis we have a node. This pi symmetry is what will create the second and third bonds in a multiple bond. So it is this pi symmetry that allows us to share more than two electrons between two nuclei. Because remember, each one of our orbitals can only hold two nuclei. So if I look at a double bond would have my initial bonding or my initial overlap of two orbitals on my internuclear axis. So typically that will be through the hybridization or the hybrid orbitals that we have. They will overlap directly on that internuclear axis. My second overlap, my second pairing or sharing of electrons will then happen with these unhybridized p orbitals, and we will see the overlap above and below the internuclear axis, or we may see them out in front or back behind. So remember, if that p orbital is coming, pointing out at you and going back behind the plane of the board, I can see the overlap then out in front of the nuclear axis or back behind the nuclear axis as well. So we can see different overlaps. We can then share 3 pairs of electrons between 2 atoms instead of just the one. So again, we have sigma symmetry, which is always going to be single bonds. It will also always be the first bond in a multiple bond. In order to generate multiple bonds, I need to have unhybridized p orbitals. And when those unhybridized p orbitals overlap, they will form our pi symmetry or our pi bonding. So I do briefly want to talk a little bit about other elements that have lone pairs of electrons. And we're going to see that hybridization of orbitals can occur in these elements as well, such as nitrogen, oxygen, phosphorus, and sulfur, some of our elements that will have lone pairs associated with them. These elements will contain sp3 hybridization, just like we're going to see with our carbon atoms when they have single bonds associated with them. The lone pair of electrons is going to show up in hybrid orbitals. So not all hybrid orbitals need to be utilized for bonding. Sometimes those hybrid orbitals will just contain the lone pair of electrons for us. This is why we see the same types of bond angles in our structures with lone pairs as we do in our structures that contain nothing but single bonds. Our bond angles will decrease with the number of lone pair electrons. So if we look at something like nitrogen, and if we have a structure like NH3 that we have seen before in your general chemistry class, that nitrogen has that lone pair on it. It is going to be sp3 hybridized. That's what accounts for the tetrahedral electron domain geometry, but the trigonal plane or the trigonal pyramidal molecular geometry because of the lone pairs. So that lone pair is going to be in one of the sp3 hybrid orbitals. We will see a slight decrease in the bond angle, so our bond angle here will be slightly less than 109.5. If we look at something like water with its two lone pairs from general chemistry, we still see the tetrahedral electron domain geometry, 4 total electron domains, 2 of them with bonding, 2 of them non-bonding, which gives us the bent electron molecular geometry. Our bond angle is still going to be less than 109.5. So our bond angle will still be less than that 109.5, but even more less than what we saw with the nitrogen. The more lone pairs we put on, the more that bond angle will decrease. How much it decreases will also be dependent upon the types of atoms that are connected to that central atom as well. So we can't really define exactly what that number will be. It will be dependent upon a variety of different things. So this is all of our hybridization theory and our valence bond theory.